In this example, we're asked to predict the shape under load of a beam that's now supported at one end and at the other end. The consequence for that support are a change in the initial conditions and at the end conditions, or the boundary conditions. In this scenario, the y value, which is how much the beam is deflected, is going to be 0 at the end. We don't let the ends move. And we also are going to ensure that the slope is 0 at the beginning, so it's clamped flat. And then we're going to apply exactly the same rules at the far end where x equals 4. The differential equation that governs the shape is the fourth derivative of y times EI, which are the modulus of elasticity and the moment of inertia of the beam, are equal to the loading in newtons per meter. And with this diagram and these conditions and the E and I values below, we're ready to predict how this beam is going to be distorted when we apply this load a little off center to this beam. Writing out our differential equation in more detail here, we're going to have a 3-element piecewise function for our load. We have 0 when x is between 0 and 1. We have a load of 9,600 newtons, that was on the previous page, when x is between 1 and 2, and the load returns back to 0 for the last part of the beam. That is our P of x in newtons per meter. Before we can take the Laplace, though, we need to restate this in terms of step functions, but again, that's fairly straightforward because we have a simple on-off scenario. The load turns on at x equals 1, the load turns off at x equals 2, and so we can multiply our 9600 by u1 minus u2, and that'll capture that on-off pattern. Taking the Laplace of the entire equation now, we're going to have e times I, s to the 4 y of s, minus decreasing s's, and s, and we'll have a constant term at the end, and increasing derivatives of y, and up to the third derivative of y here. And that's going to equal the transform of the right-hand side, which is 9600, and the transform of the step functions is simply e to the minus s over s minus u2, the transform is e to the negative 2s over s. Now we have some initial conditions that are provided. Again, the slope and the value of y at the left-hand end are both 0. These values here are a little more complicated. They're going to be based on y of 4 values, but we don't know those yet. And what we need for our equation right now is y of 0. So what we're going to do is call this A, call this B, and we'll solve for them later. Tidying up, we're going to have e times I, s to the 4 y of s, minus sa minus b equals 9600, e to the negative s over s minus e to the negative 2s over s. And now we want to hone in on the unknown function. What's the deformation of this beam? Well, that's y of x. What we have as an intermediate is y of s. Bringing the s, a, and b terms over to the other side, we have sa positive times ei plus b positive on the other side times ei plus 9600 e to the negative s over s e to the negative 2s over s. And finally we can divide through by ei s to the 4. And last here. And what that gives us, if we tidy up one last stage, canceling some s's, is a over s cubed plus b over s to the 4 plus 9600 over ei e to the negative s over s to the 5, 4 and 1, minus e to the negative 2s over s to the 5. And this is something we can find the inverse transform of. We'll complete that on the next page. Working to find the inverse transform, we note that these are all powers of t transformed, so what we're going to need are multipliers. So we're going to put a 2 over 2 here. This is going to lead to a t cubed, but it needs a 3 factorial. So we're going to group those and group those. That'll be a transform of t squared, t cubed, and likewise, all of these are going to need a 24 or 4 factorial multiplier on top. And to counterbalance that, we include a 24 in the denominator as well. And that will lead immediately to our solution. Y of x is going to be a over 2 x squareds plus b over 6 x cubed plus the transform of these terms. The leading coefficient is 400 over EI, 9600 over 24. And then each of these terms have exponentials which lead to step functions. So e to the negative s is u1, and this would be a transform of t to the 4, but it'll turn into t minus 1 to the power of 4. So that negative 1 thing there leads to 2 different effects in the transform. And similarly, the transform of the second term will be u2, because this is a 2 in here. We'll have u2 and t minus 2 in our final transform function. To make that easier to interpret, we're going to write it in piecewise format. Our function is really different on 3 different intervals this time. When x is between 0 and 1, these two u functions have not turned on yet, so all we have is a over 2 x squared plus b over 6 x cubed, and that's all we need at the beginning. Later on, when u1 is activated at x equals 1, we're going to have exactly those same terms plus the contribution of this term here, 400 over EI times t minus 1 to the 4. And that will apply for 1 to 2 for our x values, so in the domain where the load is actually being applied. On the last interval, we have the accumulation again of all the previous terms, which are still on, including the one that turned on at time 1, or x equals 1. And then, last but not least, we'll have our subtraction of 400 over EI x minus 2 to the power 4. Now, quick correction, the independent variable here is x, not t. On the interval x equals 2 to x equals 4, so this last domain here. The only remaining ingredient is to solve for a and b, and we'll complete that on the next page. In solving for a and b, what we're going to use are the end conditions. Y of 4 is 0. We're not allowed to move this endpoint here. And the slope must be 0 at that point. It's being pinned or being clamped so it remains flat. To be able to use both those conditions, we're going to need a derivative. So we're going to take the x derivative of our function on this interval. Notice that this is the function that applies when x is between 2 and 4. Most importantly, the 4 point is what we need right now. But we can take the derivative on that interval. That'll give us ax plus b over 2x squared plus 1600 over EI x minus 1 to the 4 minus 1600 over EI x minus 2, cubed for both of those. Now we can use our feature that y of 4 is equal to 0. That'll give us 0 equals a over 2 times 4 plus b over 6 times 8 plus 400 over EI 4 minus 1 to the power 4 minus 400 over EI 4 minus 2 to the power 4 2a 4/3 b. And simplifying these terms, we end up with 26,000 over EI, and that's it. Now we can use the derivative condition. That's a little easier to work with, but it'll give us 0 equals 4a plus 8b's plus 1600 over EI 4 minus 1 cubed minus 1600 over EI 4 minus 2 cubed. Simplifying that, we already have the 4a and the 8b's, and expanding this term here turns out to be 30,400 over EI. Now we have two equations in A and B, they're both linear. We can fairly straightforwardly solve those. Won't demonstrate that here, but you'll end up with A is 5450 over EI, and B is equal to a negative 6525 over EI. And that produces the two coefficients that we need to complete our model, or our function that describes the shape of this beam. To put all the pieces together, we'll go back to the functional form we had before, the piecewise form, which was this form here, noticing that the terms were a over 2 and b over 6, x squared and x cubed, and we can complete the function from there. Using a over 2, we get 2725 x squareds, and the b over 6 is a little less convenient. It works out to 1087.5 times x cubed. All of these over the properties of the material. Again, we don't have to bring these in if we don't need to actually evaluate it. And that is defined for our intervals 0 less than x less than 1. And then we have exactly the same terms again, plus the terms that we found earlier for the other two intervals. So these were defined by our a and b values, and we also had the 400 over EI terms coming from the load. This is on the interval 1 to 2 for x, and last but not least, we have all the same terms again, plus the one that applied on this interval, and then we had a last term which was negative 400 over EI, x minus 2 to the power 4, and that applied on the final stretch of the beam between x equals 2 and x equals 4. With all this information, we can actually graph the shape of this beam under this load and predict the deflection that's going to occur.